We know that global climate change is one of humanity's biggest problems, but what can we do with the CO2 that is emitted into the atmosphere? Here in Iceland, scientists are working on a solution.
Ученые испытывают одно из возможных решений этой проблемы.
Iceland largely relies on geothermal power, one of the greenest energy sources available. But the underground steam contains carbon dioxide of volcanic origin, which also ends up in the atmosphere.
Geothermal power plants do not emit a lot of CO2. For example, Hellisheiði power plant, which generates 300 megawatts of electricity, emits about 40,000 tons per year, which is around 3% of what a fossil fuel powered power plant of the same size would emit. So we do not emit a lot, but we're still trying to reduce our emissions.
Instead of emitting the carbon dioxide and other gases into the atmosphere, here it is captured, mixed with water that comes from the same steam, and then pumped deep into the ground. The technology involving the recycling of the carbon dioxide tested at the plant also can be used by other industry.
When the steam goes through the turbine, it go to condenser, where the steam is condensed and went from steam to water. And we just simply use that water to dissolve the CO2 and H2S and pump it down again, because everything which comes up, we want to pump it down again.
Powerful pumps inject the carbonated water 500 meters under the Earth's surface. This ensures that the carbon dioxide won't leak into the atmosphere.
So here we are at the injection site, where we inject the CO2 dissolved in water back into the ground. Basically, we have to make sure that it stays at a large enough depth that the pressure of the water column above the injected gas is high enough to keep it dissolved.
Iceland is composed primarily of basalt. This porous rock of volcanic origin plays an important role in capturing the carbon dioxide. It chemically reacts with carbonated water, turning the carbon dioxide into solid minerals.
Basaltic formations are good for injecting CO2 because of the chemical composition of the basaltic rock. It contains a lot of calcium, iron, and magnesium, and these ions are necessary to mineralize the CO2 in the ground.
Experiments at the University of Iceland have demonstrated the viability of this conversion method. Using basaltic powder to stimulate the underground processes, scientists initially predicted that it would take around 5 years for carbon dioxide to mineralize.
People were doing some modeling, so they were modeling big-scale injection, and then they were saying that it will take at least a few years to store the CO2 or to change the CO2 into carbonate minerals. But actually the field work now, the CO2 Carbfix project, afterwards it showed that we got it much faster. And this exceeded our expectations. So we are very happy about this, that we could store it. And this is actually wonderful news for us, for scientists, and for the people, because we can fix the CO2 and do something with our climate.
These core samples show that the carbon dioxide converted into solid calcite in just 1 year, significantly faster than scientists forecasted.
Here in the core we can see the white spots. These are calcium carbonate precipitates, showing us that the injected CO2 has mineralized, turned into stone, and thereby we have immobilized it permanently.
But what about byproducts of this method? Is it safe for the groundwater? So far, scientists working in this European research project haven't found any reason for concern.
We take samples and analyze them for trace metals to make sure that we are not contaminating the water. And in this experiment, all the samples have been within the drinking water limits.
Города завтрашнего дня
Tomorrow's
будут
cities will increasingly rely on alternative energy options. Today's windmills produce a lot of noise, aren't very bird-friendly, and are often located far from end users of their energy. But there's an urban solution.
This futuristically shaped apparatus in Porto's marina uses solar panels and small wind turbines to generate power locally.
It works like a wing that turns the wind flow from horizontal to vertical to rotate the central turbine and generate energy.
The highly efficient solar panels generate energy wherever there's sunlight, and the horizontal rotor blade works independently of wind direction.
With this device, you can power your house with your own local energy, without using the electricity from the grid that might come from coal or even nuclear power plants, so you can contribute to sustainability.
Supported by a European research project, this technology is marketed for various applications. In the city, it can power electronic equipment independently from the urban electrical grid, which can be complicated to plug into.
Nowadays, you need to dig cable trenches in the ground to connect your equipment to the grid. You need authorizations, which you sometimes don't get in time. So it's much easier and faster to use this solution to provide electricity on the spot.
The batteries, hidden under the shell of the device, store the generated energy. Various components can be added depending on the specific need.
The empty space inside allows us to install all kinds of electronic devices which can, for instance, provide wireless connectivity in rural areas. We can install antennas to provide mobile internet in remote places.
As the sun sets in Porto, one of the brightest applications of this technology becomes evident. The intelligent LED lighting automatically turns on, using accumulated energy to illuminate the marina.
What we have here is the prototype system. A single unit isn't enough to make much difference. But you can imagine 100 of such devices that will generate 15 megawatts per hour of power per year, contributing to the city. In Bedford, England, a cleaner and quieter alternative to modern airplanes is taking shape. The creators of the Siemens airship soon expected to take the skies, defying the means of aerial transportation.
Called Airlander, this hybrid airship combines several aeronautical technologies, including some used by planes and helicopters to maximize its efficiency.
The hull has got 38,000 cubic meters of space inside it, which is mainly filled with helium, lighter than air. That gives it lift, and about 60% of its lift comes from that. Up to 40% comes from having a wing shape, having an aerodynamic shape, and that gives it extra efficiency and means it's very controllable.
This test flight, made by a prototype version of Airlander, demonstrated good flight capability. At 150 kilometers per hour, it doesn't move very fast, but it can remain safely buoyant for weeks and doesn't need airports to take off and land.
So we can do deliveries into places that have got runways that perhaps have got no runways, or perhaps there's been damage in a natural disaster or something like that. So a bit like a helicopter, but much, much bigger and more efficient. We use helium, not hydrogen. Helium is an inert gas, It doesn't explode, it doesn't set on fire, it won't support a flame. We've also got lots of different ways of lifting this aircraft. So some of our lift comes from buoyancy, some of it comes from aerodynamics, some of it comes from the vectored thrust of the engines. So we've got lots of redundancy and lots of safety in the way that we operate the vehicle.
The Airlander will be capable of transporting up to 10 tons of load. Its next version will have a capacity 5 times bigger, on par with cargo planes, but with much better fuel efficiency.
If we were using a 21-day mission, which is what the old vehicle could do, we would use as much fuel as a fighter jet would use in 1 hour, and we'd stay up for 21 days non-stop. So it's a significant difference in the amount of fuel used, for sure.
Engineers expect hybrid airships to become a popular way of transporting cargo when high speeds aren't required. They can be the best choice for long-term observation missions, or can even serve as luxury hotels in the sky, with minimal atmospheric pollution.
We're already a quarter to a third of the emissions of other aircrafts. But in the future, we should be going all electric and having solar panels on the surface of the aircraft, which will make us a zero carbon aircraft. And that will truly revolutionize the emissions problems that aviation are causing at the moment.
Climate change is a tough challenge, but new engineering alternatives and scientific solutions can lead the way to a brighter and greener future.